Welcome back to the class on a power semiconductor price. In this class, we are going to discuss about the three-phase off-control converter with a DC motor load by taking the firing angle greater than the 30 degrees. This firing angle alpha equal to 90 degrees. In the last class, already have seen the circuit diagram for the three-phase off-control converter with a DC motor, T1, T2, T3, D1, D2, D3. So to develop the output voltage waveform for this circuit, we have taken alpha equal to 90 degrees. First of all, we have to represent the six line voltages. At 0 degree, we have taken the one vertical line. This is the x-axis. On x-axis, we have taken the angle. This is the positive maximum line voltage. This is the negative maximum line voltage. At every 60 degrees, you have to take the one vertical dotted line up to the 360 degrees, because we are going to draw the input voltage within the 360 degrees. First VAB voltage, next VAC voltage, next VBC voltage, VBA voltage, next VCA voltage. Lastly, we have drawn the VCB voltage. Now we are going to identify that what instant the T1 is on means from the 60 degrees, the T1 is forward bias. Here we have taken the firing angle alpha equal to 90 degrees. So 90 plus 60, nothing but a, at 150, the T1 is on. Once it is on, it has to conduct a 120 degrees. So next T2 has to conduct. Here 90 degrees, remaining 30 degrees starting. Next remaining 120 degrees, T3 has to conduct. Now we are going to identify the what is the region in which diodes are conducting. 0 to 120 degrees, B phase is more negative, so D2 is on. So 120 to 240 degrees, C phase is more negative, so D3 is on. 240 to 360 degrees, A phase is more negative, so the D1 is on. These are the conduction region of the diode, which is not depending upon the firing angle as like the SCRs. Now we are going to identify the two devices, because from the upper group one device has to conduct, from the lower group one more device has to conduct, then only there is a closed path between the load and the source. Then the power is passing from the source to the load. So 0 to 30 degrees, the T1 D2 is conducting. Next T3 D2 is conducting. Next in this interval T3 D3 is conducting. Here from this point to this point, T1 D3 is conducting. Again in this duration, T1 D1 is conducting. Again from this point to this point, T2 D1 is conducting. Here you try to observe here on the same leg, the two devices are conducting means is simply making a short across the load. Suppose if we take the T2 DT is conducting. In this interval, T2 DT is conducting. So taken the load current is constant load current. Now the load current will be passing from the D2, T2 and load in this manner. Nothing but a, so previously how much energy stored in the inductor, that energy will be taken by the load itself. This action is nothing but a freewheeling action. So when the freewheeling action is taken place, the load voltage becomes a 0. The same manner, suppose if the T1 D1 is conducting, the load voltage becomes a 0. The T3 D3 is conducting, the load voltage becomes a 0. Because we are going to develop the output voltage wave. On the x-axis we have taken the again angle, but we started from this instant where the T1 D3 is conducting. The T1 D3 is conducting T1 D3, nothing but the output voltage becomes VAC. Go up and see how the VAC is changing, nothing but from this point to this point. Maximum to 0. Again T1 D1 is conducting. T1 D1 is conducting means now the load current is passing in this manner. Nothing but there is a freewheeling action taking place across the load. So the load voltage becomes a 0. So here the load voltage 0. T2 D1 is conducting. If the T2 D1 is conducting, T2 D1, nothing but the output voltage becomes a VBA. Go up and see again from this point to this point. So you take up the same voltage waveform. T2 DT is conducting, again the output voltage 0. T3 D2 is conducting, the output voltage becomes a VCB. Go up and see VCB voltage. You take up the same thing. This is the VCB voltage. So if the firing angle more than the 30 degrees in a half control converter, some duration the load voltage becomes a zero. There is a discontinuous in a output voltage, but the current is constant. We have taken the load current is a constant. This current is nothing but a here. This current is nothing but a freewheeling current that we represent with IF. This current from this point to this point, this current is nothing but a ICB. Again from this point to this point, here IF. Again in this interval, IAC. Again in this interval, IF. Again in this interval, IBA. This is the output current waveform. When the freewheeling action is taken place across the load, the current is not given by the source. The current will be passing through the load due to the energy stored in the inductance. During the freewheeling action, the source current is zero. Now we are going to draw the phase current, that is the phase A current. So from this point to this point, the phase A is not supplying any current. Again, in this duration also the phase A is not supplying any current. In this interval also the phase A is not supplying any current. From this point, the phase A is supplying current. Again here 0. Again the phase A is supplying. So if you find the variation of output voltage versus the firing angle, already we derived the expression of the output voltage previously. We can take the same expression. The average output voltage V0 equal to 3 VML by 2 pi into 1 plus cos alpha. Suppose if we take the here we have taken the one table serial number alpha output voltage. If alpha equal to 0 in this expression, if you substitute alpha equal to 0, then this value becomes a 3 VML by 5. Because if cos alpha becomes a 1, here we are getting the 2, these 2 get cancelled. If alpha equal to 90 degrees, now this value becomes a 0, then the output voltage becomes a 3 VML by 2 pi. If alpha equal to third reading 180 degrees, then the output voltage is equal to 0. Now if we take the firing angle, here I am drawing, if we take the firing angle on the x-axis, this is 0 degrees, this is 90 degrees, this is a 180 degrees. Average output voltage on the y-axis, nothing but V0. At 0 degrees, the average output voltage becomes a 3 VML by 5. At 90 degrees, 3 VML by 2 pi. Here. This magnitude will be less than this one. At 180 degrees, it becomes a 0. If you line join all these points, you are getting that. This is the variation of the output voltage versus the firing angle. The three-phase off control converter for the constant load current. For the range of firing angle from 0 to 100 degrees, the average output voltage is always positive, the current also the positive. So between the load and the supply, if you use a three-phase fully controlled converter, it is giving only the motoring operation, nothing but it gives only the one quadrant operation. It does not give any, we cannot apply any braking to the motor by means of this. Suppose if we want to apply any braking to this motor, we can't apply any electrical braking. You can go for the mechanical braking. So some loads requires only the motoring operation. By the time you can use this circuit to control the speed of a motor. It is very cheap when compared to the three-phase fully controlled converter. That's why we are studying the three-phase off control converter with a DC motor load. Thank you very much. If you have any doubt, you can ask me directly or you can ask me the comment box of my YouTube channel so that I can answer all your